So let's remember what we were talking about. 5.4, inner product spaces. Right. So basically, we're taking the abstract vector space, and we're putting something on it that's like a dot product, right? So you have some vector space, and you have this thing, bracket, which behaves like the dot product. Okay, in the sense that it's commutative, right? Xy equals yx. It's got a distributive property, right? It's linear in the first variable. Ax plus beta y comma z equals alpha x against z plus beta y against z, right? And then we also have this positivity condition, right? That x against x is always greater than or equal to 0, and is 0 if and only if x is the 0 vector. So that's what an inner product is, and we gave some examples. And so the theme is basically sort of like the geometry in R2, in Rn carries over to inner product spaces. Okay, so I think the one that you want to keep in mind, or one of the things you want to keep in mind is this, like you got continuous functions on some interval. We define the inner product of two functions. We define the inner product of two continuous functions as just the product, the integral of the product, right? Yeah, that's kind of a right, like this is very non-Euclidean, right? This is very non-Euclidean, so it keeps you thinking like, okay, this is not necessarily anything like what we were doing before. Okay, so so geometric concepts carry over. So geometric concepts in Rn carry over to inner product spaces. So first, if you have two vectors, then we can define that they're orthogonal, right? So suppose you have two vectors in an inner product space, then what am I going to say? They're orthogonal if, we'll call them orthogonal if what?
Their dot product is 0.
Yeah, their inner product is 0.
Sorry,
yeah, so if their inner product is 0, we say that they're perpendicular to each other. U and V are orthogonal. Okay, so here's an example. If we're looking at continuous functions on -1, 1, and we look at the integral from -1 to 1 of x times 1 dx, right? We're just integrating, we're integrating the function x from -1 to 1. Well, that's 0, right? That's 0. Right, and what that tells you is that the function x and the function 1 are orthogonal to each other. Right, these guys are orthogonal, right, because their inner product is 0. Another example, if you take over negative pi cosine x against sine x, then that also turns out to be 0. Okay, so cosine and sine are orthogonal on in the continuous functions from negative pi to pi. Okay. Okay. So orthogonality. We can, in an abstract vector space, as long as we have an inner product, we can talk about things being perpendicular to each other. Another thing we can talk about is a notion of magnitude. So if you have some vector v in an inner product space, we define the norm of little v as what am I going to say? How do you define magnitude in terms of the dot product?
It's dotted itself.
Dotted against itself, and then you take a square root.
Yeah.
So same thing. We're going to take the inner product of the vector against itself. I'm going to take the square root of that. So you can talk about the size, the size of a function. If I look here, if you take the cosine against the cosine, it turns out to be 1. So the magnitude of the cosine and the sine are both 1. So okay. Once we have the idea of norm, we can define the idea of projection. Projection of one vector onto another. Okay, so it's basically just a generalization of the Euclidean idea. So, given two vectors, u and v, in some inner product space, we define the vector projection. We usually just say projection. We define the vector projection of u onto v as u inner product v over v inner product v times v. Okay, that might not look like what you remember when we defined the projection out before, but it actually is. If you think this is u against v, and then this thing is the norm squared of v, right? This thing here is the norm squared of v. So I'm going to put the norm of v here, and then I'm going to put another copy of the norm of v here. Okay. Now I hope it looks more like what we said before about the inner product, about the scalar, about the vector projection. Right, right. This is, remember, this was that you had some u, you had some v, right? You have the direction of v, that's this thing, right? This is the direction of v, and then we calculated, geometrically, the scaling constant here was this constant, right? Okay. This is what we called the scalar projection. of u on v. Right. That's why this thing is called the vector projection. This is the scalar projection. Okay, but again, this is good because, I mean, it seems kind of strange, but we can talk about the projection of one function onto another function. Okay. Okay, so those are some concepts, sort of geometric concepts that we can extend into any space with any vector space with an inner product. They're also sort of like geometric results that also occur in inner product spaces. So first off, we have a Pythagorean theorem. Okay, so that should seem kind of strange, right? Where are the triangles? Right, there are no triangles, right? Because if there are no triangles in our space of functions, right? But we can still talk about a Pythagorean theorem, right? So V, an inner product space, and you have two vectors u and v in there. So if u is perpendicular to v, then what does the Pythagorean theorem say? If you've got two vectors that are perpendicular to each other, then you can say something about, wait. Oh.
Just like the square root of the product of their squares.
The
square root of u squared is the square root of v squared.
So, right, the length of this guy, right, the length of this guy, and the length of this guy, and we have, this thing here is u plus v, the vector, right?
Mm-hmm.
So it's going to be, right, the c squared equals a squared plus b squared. Right. Okay, but let's think about that. So just by definition, u plus v. Maybe I'll let you do it. Okay, see if you can take 1 minute and see, just look at what these things are and see if you can work it out. I think you can definitely do it. Okay, anybody figure it out? No? Anybody figure it out? No? Okay. Do you talk to each other? Did anybody talk to each other? No? Talk to each other. I'll be back in a minute. 1 minute.
What we're trying to find, like for like that, which I can separate, I'm not sure. But I'm product space. Maybe that's fine. And then that's, does it have to do with any product, you think?
Product of.
Because,
I feel like if we're talking about the norm and projection, it has to do with that, but I can't figure out.
wait. So if the norm is the square root of the product squared together.
Yeah.
The squaring of that, it just means that
Oh, okay.
it's like the inner product of u dot u plus the inner product of v dot itself.
Yeah.
But I guess that's just like commutative.
Right.
You know what I mean? Like I don't.
Yeah, yeah.
Like what are we trying to say? So, oh, because that's a property of the inner products too,
Oh,
right? Like, yeah, or
then,
I mean, basically. Big not really.
And then I think what I've heard of this, but then because E and B are
It says you can switch them, it doesn't necessarily say we could, because what we have is like, u plus v, if it were on the right hand side, but I don't know what the other one takes out.
U plus B, and then common root plus B. Yeah, I don't really know where to go from there.
Yeah. Because what if they're perpendicular, then I guess their own inner product is 0.
Your own inner product?
Yeah.
Oh,
Because basically what we're doing, I think.
yeah. Oh, yeah. Wait, then isn't that just like into something? Because this would be breaking down to like u squared plus 2uv plus, and this would be 0. So, you know, and then you just got.
I don't know if we have it exactly, but I think
But yeah, I feel like
good
that's-
idea of what's going on.
Yeah, that's a good guess.
Because.
Hi, sorry, I took too long. I started talking with another professor who had let his students talk to each other. Okay. Okay, so yeah, anybody get an idea? Kate?
I think so.
Yeah.
So you can like expand that up to be the inner product of u plus v with u plus v.
Exactly.
Yeah, and then I split that into the inner product of u with u plus v and then plus v with u plus v. And then I split it up one more time to the inner product of u with itself, 2 of the inner product of u and v, and then the inner product of v with itself. And then because u and v are perpendicular, the inner product of u and v becomes 0. And then that is just like the u. Yeah. move on.
There you go. I give you 2 points on the exam for that. Yeah, exactly. Right. Yeah. So Pythagorean theorem, right? So, right. So, right. Even though we don't have triangles, we do have a notion of orthogonality, and that's enough. That's enough for. That's enough to get the Pythagorean theorem. Okay. The next thing we're going to go for is the Cauchy-Schwartz inequality. Cauchy-Schwartz inequality. Okay. Does anybody remember the Cauchy-Schwartz inequality? From, yeah, that's kind of an odd one. Most of the time, you don't encounter it in Calc 3. But what it says is that that the size of the dot product is controlled by the product of the magnitudes. Okay, like the dot product of two vectors is controlled by the size, the product of the magnitudes, right? So u dot b is controlled in size by the product of the magnitudes, right? And you may recall we had this geometric interpretation of the dot product, right? It's the product of the magnitudes times the cosine of the angle between them, right? Cosine of the angle between those two vectors. So that, immediately implies the Cauchy-Schwartz inequality. But what do we mean by the angle between two functions, right? We don't have a geometric interpretation of the inner product, right? So in this case, we can't use this geometric interpretation, which relied on like the law of cosines and stuff like that. Okay. So, but it's still true. Okay. So if you take two vectors in an inner product space, then in fact it's true that the size of the inner product is controlled by the product of the magnitudes. Right. And secretly, so notice one thing. To show that, so here's a sort of side comment. Remark. If A and B are positive numbers, then for A to be greater than or equal to B is the same thing as A squared to be greater than or equal to B squared. Right? If you're dealing with positive numbers and you're looking at squares, right? You're looking at squares, right? If you know that A is greater than or equal to B, then you definitely know that A squared is greater than or equal to B squared, right? And similarly, right, conversely, if you know that A squared is bigger than B squared, you know that A must have been bigger than B. Okay. It's not true if you're talking about like negative numbers also, right? Because you can have, A over here and then B over here, right? Like A squared would be bigger than B squared, but the A would be less than B, right? But for positive numbers, it's true. Okay. The point of this is that so this thing that we're trying to show we can actually show this thing is equivalent to this thing. Okay, is equivalent to this thing. So if we wanting to show this is less than or equal to that is the same thing as showing that this squared is less than or equal to that squared. Okay, and maybe from there you start to see the I don't know. No, actually, anyway, so I'll just leave it at that. Okay, so, okay. So let's go for the Cauchy-Schwartz theorem now. And it relies on, so the proof requires two lemmas. The proof requires two lemmas. Okay. So here they are. Say that V is a non-zero vector, and that, say that U and V are in capital V an inner product space, that V is non-zero, and let P denote the projection of U onto V. Okay, so vector, vector, vector U, vector V, and then you have this P, which is a projection of U onto V. Okay. So lemma 1 says that U minus P is perpendicular to P. Okay, right, in the picture, which doesn't exist, this is U minus P, right? This is P, this is U minus P, this guy here, right? This is P, this is U minus P, and then add them together and you get U, right? Is that okay? Right, or if you want to think, you've got U, you've got P, you've got minus P, right? U plus minus P is this guy. U plus minus P is that guy, which is this thing here, right? Which is this thing here. Right. Okay, so first claim that U minus P is perpendicular to P. Okay, so let's just see how that works. So U minus P, remember what P is. P is U inner product V over V, inner product V times V, right? And we want to take the inner product of that against the projection. Okay, you're hoping that this is equal to 0, right? You want these guys to be perpendicular to each other, right? U minus P and P. Okay, so you say, okay, this turns out to be just a straightforward calculation. So you say, okay, we're going to break this into pieces. This is going to be U against U, V, 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 and then minus U, V, V, inner product V, V against itself. Okay, this is not really an exciting thing. I'm tempted to just say, work it out yourselves, but this is a constant here, right? These things are just numbers, so we can pull them out, right? We can pull them out. We get that constant And then what we have here is u against v. That's what's left, just u against v. Over here, we have the square of that constant. Right? Right? And then we have v against v itself. And you see that it works out, right? This cancels with that, and we get something minus itself. We get a number minus that same number. So boring. Okay, so the proof of that is quite dull. Okay. Part 2. Lemma number 2 is that u equals the projection of u on v if and only if u is some scaling of v. Right? So u is equal to its projection if and only if it's some scaling of v. Okay. So pictorially, what this is saying is that if this is u, if this is v, and u equals, the only way that u could be equal to its own projection is if it's on v to start off with. Right? The only way u could be equal to its projection on v is if it is on v to start off with. And that's kind of an obvious statement. Okay, at least here, and we just want to make sure it's true, abstractly. So proof. One way forward is obvious, right? Okay. If u is its projection, definitely it's a multiple of v. Right? So that's obvious. Right? Because the projection is some multiple of v. Right? Okay. Going backwards, if u equals some multiple of v, then when we look at the projection of u onto v, well, we're going to get u against v, v against v, v. But we can pull that beta out, and you see that we just have 1 left over. We just have 1 left over, right? And so we get beta v. Okay, right, which is u. So going backwards, right, if u is a multiple of v, then u is equal to its projection onto v. Okay, so these are kind of straightforward statements. Okay, let's get to the Cauchy-Schwartz lemma, Cauchy-Schwartz theorem now. So proof of Cauchy-Schwartz. Right? We want to show that the size of the inner product is controlled by the product of the magnitudes. Okay, and like I said, that's the same thing as showing that the squares of both sides, satisfy that same relation. Okay. Oh, actually, first note that if v is 0, then this is obvious, right? If v equals 0, what's the left-hand side here? 0, right? You're just going to have inner product of something against 0. That's going to be 0. And then the right-hand side is going to be 0 also, right? So definitely that's true, right? 0 on the left-hand side is less than or equal to 0 on the right-hand side. Right? So now, we can assume that v is non-zero. Okay, so I'm going to divide both sides now by magnitude of v squared, which is okay because v is not 0. Okay, so this is what we want to show, right? Right? We're trying to show this, which is equivalent to this, which is equivalent to this. Okay, so this is what we're trying to show. What's this thing on the left-hand side? Anybody recognize this thing on the left-hand side? It should look kind of familiar. Like, within 5 minutes familiar. What was the projection of u onto v? Gonna be I'm going to write it this way. It's this thing here, right? So what is this thing right here? This is actually the norm of the projection squared, right? Because when you take the norm of this thing, well, this is just 1, right? The size of this is 1. You pull out this constant, you get absolute value of uv over norm of p, right? So this thing on the left here is the square of that. Okay, so our question is, we want to show that the norm of the projection of u onto v squared is less than or equal to the norm of u squared. Okay, so this is u, this is v, this is projection of u onto v, right, which we call p, right? This is u minus p, right? So we want to show, right, that u squared is bigger than or equal to p squared, norm of p squared. Norm of u squared is bigger than or equal to norm of p squared. Why is that true? Talk to a neighbor for 1 minute, and I'll be back in 1 minute.
What's normal is that if u is its own projection, then
I was thinking about
it's just like the constant times v.
I mean, I guess it would be.
So it's like if we also, so I guess it would like.
Yeah.
That's
I think that's.
Okay. Okay. Anybody see why this is true? Why is if this is p, this is u, and this is u minus p, why is the norm of u squared bigger than or equal to the norm of p squared? What's the relation between the norm of u squared, the norm of p squared, and the norm of u minus p squared? The Pythagorean theorem, thank you, right? You know, we still have the Pythagorean theorem, right? U squared equals p squared plus u minus p all squared, right? So by the Pythagorean theorem, we've got this, right? So, so definitely, so u squared is definitely greater than or equal to p squared, right? Because u squared is p squared plus something else, right? Right. Okay. Further, u squared equals p squared if and only if u minus p is 0, right? In other words, i.e. u is the projection of u onto v. Okay, so at this point here, we've got the Cauchy-Schwartz inequality, right? Because to get Cauchy-Schwartz was simply to say that this guy is bigger than its projection. But we know it's bigger than its projection because it's equal to the square of the norm is equal to the square of the norm of this plus the square of something, something positive, right? So one, we have Cauchy-Schwartz. 2, we've also shown that Cauchy-Schwartz inequality becomes an equality if and only if u equals projection of u onto v. Right, that's this further thing. Further, we have an equality if and only if this term vanishes, right? If and only if this term vanishes, right? But that would mean that u equals the projection of u onto v. But we had that lemma that said that happens if and only if u is some multiple of v. Okay, so that's actually the full Cauchy-Schwartz theorem. Okay, I always forget the second part. I think the second part of the theorem is often forgotten. I forgot it just now. But Cauchy-Schwartz has 2 parts actually. It says 1, that the size of the inner product is controlled by the product of the sizes. 2, that those guys are to be equal to each other if and only if one of them is a multiple of the other. Okay, yeah. And so it's funny, Cauchy-Schwartz is really just this statement that this length is bigger than this length, right? Which is kind of an obvious thing. That's Cauchy-Schwartz right there. This length is bigger than that length. Okay. Wow, where did the time go? Gosh, a second ago I thought, okay, I can do a little bit more. I can do a little bit more. Sorry, I'm just going to do one more thing. One more tiny bit, which is that, so now we can do something really peculiar, which is given two vectors in an inner product space, we define the angle between V and W. I'm sorry, between U and V, to be the arc cosine of the inner product of U against V over the product of the magnitudes. Okay, so we can talk about, now we can talk about, the angle between two functions. Okay. And this only makes sense now because we know that we can only do this. We can only do this because Cauchy-Schwartz tells us that the size of that number is less than or equal to 1, right? That these numbers lie between -1 and 1, and so it makes sense to take the arc cosine, right? If we didn't have Cauchy-Schwartz, we wouldn't know that this number is between -1 and 1. So taking the arc cosine of it wouldn't make any sense. Okay, but now because of Cauchy-Schwartz, we can say, okay, now we're going to sort of like define the angle in a backwards way, right? So previously, we had that U dot V equals the product of the magnitudes times the cosine of the actual angle between them, right? But now we're going to say, okay, so in the Euclidean world, it is true that the cosine, the angle is the arc cosine of U dot V over product of magnitudes, right? But now we're going to use that fact in Euclidean space to sort of like, force an idea of angle onto our abstract inner product space, which is a little strange, but we do it. But oddly, we actually never use this idea ever again in this course. So I'm not sure what the point of this is, but you can do it. You can do it at least. Yeah, I guess it sort of goes along with the theme of like extending geometry to inner product spaces. Right, now we can talk about angles also, but we don't. Okay, that's it.